Okay, Francesco, when you want.
Okay, thank you. So first of all, I would like to thank the organizers for inviting me to speak here today. It's also a great pleasure because I was one of the former organizers of this Geometry and Tacos. So I mean, it's very great to be here today. So in this talk, I'm gonna report about a joint work with Cristiano Spotti, Simone Calamai, and Daniele Angella about a moment map for twisted Hamiltonian vector fields on lcK manifolds. Okay, so first of all, before going into the details of the work, I would like to spend some words about the moment maps. So, what they are and why do we care about them? So to begin with, we can consider a compact Lie group together with a symplectic manifold. So let me recall that the symplectic manifold is a pair given by a smooth manifold and a closed non-degenerate two form on M, okay? We assume that the group acts on M smoothly, okay, effectively, and that it preserves omega. So the fact that it preserves omega allows us to consider the fundamental vector fields associated to these actions by taking the derivatives. And these fundamental vector fields are going to preserve omega as well, okay? So we can identify the Lie algebra of G with a set of those vector fields on the manifolds that preserves omega. Actually, an easy computation shows that the fact that a vector field X preserves omega is equivalent to the fact that the one form that you get by the contraction of X with omega is the closed, okay? So in particular, if you assume, for example, that your manifold is simply connected, then for any vector field X in the Lie algebra of G, you can find a potential, meaning that you can find a function H such that the one form that you get by taking the contractions of omega and X is the differential of this function. And actually the potential is is like uniquely determined up to an additive constant. Okay, well, then a moment map, by definition, is just, in a sense, like the dual of the correspondence that takes a vector field and gives you the potential of these vector fields with respect to the symplectic form. So to be more precise, a moment map is a smooth map which is equivariant with respect to the action of G, takes values on the adjoint of the Lie algebra of the Lie group G, and that verifies the following equation. So that whenever you take the actions of mu against a vector field on the Lie algebra, you get a function, you take which is precisely the Hamiltonian potential of the vector field X. Okay, so the differential is going to give you the one form obtained by the contractions with X. So why is it important to have a moment map in symplectic geometry? Actually, it has a lot of applications. And for example, one of the main applications of moment maps is the fact that they allow you to construct good quotients. And these also like establish a bridge between the symplectic geometry and the geometric invariant theory, which is a branch of algebraic geometry that studies like actions of algebraic groups, and in particular like allows you to take quotients even when the topology is bad in a sense. So like the link between like the moment map in symplectic geometry and the possibility of taking good quotient via the geometric invariant theory in the geometric invariant theory framework is given by the fact that whenever you have a moment map, okay, you can consider the zero level set of the moment map, and actually the compact Lie group G is going to act on this set, and this set parameterized the closed orbits or stable in the nomenclature of a geometric invariant theory with respect to the complexified action of G. Okay, So here in general, G is compact, so the complexified Lie group is well defined. So let me give you like the basic examples of this picture. Okay, this is like the most famous examples that you find on all the textbooks. So as a manifold here, you consider C2, and as you consider the action of the complex Lie group, which is C minus the origin acting on C2 in this way. So you have lambda, and you define the multiplication of lambda times a vector xy in this way. So the first component, you multiply by lambda, and in the second component, you multiply by lambda minus 1. Okay, so it's easy to describe the orbits of these group actions, and actually in this setting you can find basically three types of orbits. So the first type of orbits are what are in green in this picture, and are the hyperbola xy equal to t for some values t different from 0. These are one-dimensional orbits and they are closed. Then you have another orbit, which is the origin, containing just 1 point, 0, 0. Again, this is a closed orbit, and it is zero-dimensional. Then you have also other two orbits that are the two axes in blue without the origin. And these are, again, one-dimensional, but they are not closed. And in particular, the closure contains the red orbit. So, of course, if you want to consider like the standard quotient of C2 with respect to this action, this is not a good quotient because it's not going to be Hausdorff. I mean, in the quotient space, you cannot separate the closed zero-dimensional orbit and the non-closed one-dimensional orbits. So the point here is that if you want to obtain like a good quotient, a quotient with good properties, what you can do, I mean, like morally, is that you discard the non-closed orbits that are the two axes, okay? And then you just consider the set of closed or stable orbits, and you can immediately see that they are parameterized by C. So in a sense, like the good quotient of this group action should be considered as C. So how can we relate like this picture with the moment map? Well, actually, C2 as a standard symplectic form, okay? You consider the maximal compact subgroup of C minus 0, which is the circle group U1. And it is actually a matter of fact that U1 preserves the standard symplectic form of C2, and you can write explicitly a moment map for this action, which is given by mu of xy equal to norm of x squared minus y of x squared. So now, if you take the zero-level set of this moment map, you can immediately see that this set intersects each closed C minus 0 orbit in a U1 orbit. And if you take the quotient of the zero-level set by the action of U1, you get C, which is precisely the quotient, the good quotient that you expected. Okay, so I mean, this was like, so this is like a very important tool in symplectic geometry. So like the idea now is that, so why should we care about these things also in non-symplectic geometry, like in other settings? So the point is that there's this general principle that whenever you're studying a differential geometric problem related, which has a well-defined symmetry group, then sometimes what happens is that the curvature in some form appear as a moment map with respect to this symmetry group. And this allows to simplify the problem and sometimes to get also like some non-trivial solutions. The first attempt in the literature where this moment map approach has been used, like outside the realm of symplectic geometry, as far as I know, is due to Ati and Bott in '83, where they studied Young-Mills equations on Riemannian surfaces. Then later on in the '90s, Donaldson and Fujiki applied this moment map picture to study the CSCK equations on compact Kähler manifolds. And later on, in 2003, Loretz used this moment map framework to study Einstein equation on Lie groups. Well, actually, I mean, the things you can get by using this moment map approach is that, first of all, it gives you a sort of unified viewpoint of many different problems. And you also can use some algebraic tools coming from GIT to study these problems. And sometimes it also like gives you some insight into what you should expect or what you should not expect about the problem that you are studying. So for example, let me just mention that tools coming from GIT allows a great understanding on homogeneous Einstein metrics. So for example, 2 years ago, this type of approach allows the solutions of the Alexievsky conjecture, saying that by Böhm and Lafuente, saying that any Einstein homogeneous manifolds with negative scalar curvature is a solved manifold. And also, I mean, like in complex geometry, also like it has been used a lot to study CSCK equations. So for the purpose of this talk, we're gonna focus now on the Donaldson-Fujiki framework because it is precisely the framework that we would like to generalize in order to study lcK geometry. Okay, so in the CSCK framework that we're gonna see in a moment, the idea is that the GIT comes not directly in the manifold, but on an infinite dimensional manifold that is attached to our original Kähler manifold, so that in principle you cannot like apply these algebraic tools like directly as a black box, but still gives you good insight into what you should expect. And we're gonna see it in a moment. Okay, so let's focus on the Donaldson-Fujiki framework. The idea is the following. So you fix your compact Kähler manifold given by MJ and a fixed Kähler form. And like in a sense, you would like to interpret the curvature, and in particular here the scalar curvature, as a moment map for a certain infinite dimensional Lie group action on the Kähler class. So here, of course, as I said before, like in principle, you expect the curvature to be a moment map. And since here we are in Kähler geometry with a fixed scalar class, the standard candidate that one can think of is a scalar curvature, which is just a function. Well, there's a little issue, and the issue is that, as far as I know, there is no way that you can see directly an Hamiltonian action on the Kähler class itself. Okay, so in particular, it is not possible. I mean, it seems that it's not possible to do this approach directly. And here comes the trick. So by using Moser's theorem up to the choice of a diffeomorphisms, we know that if you fix a Kähler class and you move the Kähler representative while keeping J fixed, it is actually the same of keeping your Kähler form fixed and moving the complex structure in a certain way. Okay, and this actually seems to be like the right things to do in order to get a moment map. And therefore, what you do in this framework is that you fix a form, which is going to be your Kähler form, and you move the complex structure in a way that it is compatible with this form. Of course, since you want your omega to be Kähler in some sense, you need to ask something. So you ask that omega is symplectic, which is a condition which is necessary for being Kähler. Okay. So actually, the construction of the Donaldson-Fujiki framework goes like this. So you fix a compact connected manifold of real dimension 2m, and you also fix on M a symplectic form, which is again non-degenerate and closed. Okay. And then you can consider the automorphism group of this structure, which is made by those diffeomorphism that preserves omega. Now, this group here is, I mean, unfortunately, in some sense, maybe not, I don't know, is not a Lie group in the general sense, because the underlying G structure of the symplectic form is in some sense weak. It's not as strong as a Riemannian metric or a complex structure at all. But you can think about this group in a precise sense as an infinite dimensional generalization of a Lie transformation group. So in particular, it makes sense to speak about the Lie algebra of this group. It makes sense to speak about the exponential map, the adjoint representation, etc. Okay, and in particular for this group here, the associated Lie algebra is the Lie algebra of those vector fields such that the contraction X with omega is declosed. Well, a distinguished Lie algebra of these infinitesimal automorphisms is given by the Lie algebra of Hamiltonian vector fields that are precisely what we saw in the first slide. This is made of those vector fields on the manifold such that the contraction X with omega admits a potential, which is called Hamiltonian potential. Well, actually, this Lie algebra gives rise to another infinite dimensional generalized Lie transformation group, which is called the group of Hamiltonian diffeomorphisms, which is defined as follows. So you say that a diffeomorphism of the manifold is Hamiltonian if and only if you have these diffeomorphisms, you can find an isotopy between the identity of the manifold and these diffeomorphisms, such that the corresponding time-dependent tangent vector field of this isotopy is Hamiltonian for any time. Okay, it can be checked that this defines a well-defined Lie group, infinite dimensional Lie group, and this is gonna play the role of our symmetry group for our problem, actually. Well, moving forward, we say that an almost complex structure on the manifold M is compatible with your fixed symplectic form if the following two conditions are satisfied. So first of all, you ask that omega is of type 1, with respect to J, meaning that if you compose omega with J in both entries, you end up with omega itself. And the second condition you ask is that whenever you compose omega with J on the second entry, you get asymmetric, you might make asymmetric 0 to tensor, and you ask it to be positive definite, so that it gives you a Riemannian metric on the manifold M. Well, actually, you can consider the set of all the almost complex structure of M that are compatible with omega in this sense, and also the subset J omega of those almost complex structure that are integrable. Well, actually, it turned out that the first of these two sets, so the sets of almost complex structure that are also compatible, is not a finite dimensional manifold, but can be as a natural structure of infinite dimensional smooth ELH manifold. So here ELH stands for inverse limit Hilbert, which means that it is a smooth manifold whose local model is a vector space, which is the inverse limit of Hilbert spaces. Okay, this is a stronger condition than being just Frechet. On the other hand, the set of integrable complex structure, well, I don't know if it is possible to endow it with a smooth structure itself, but for sure it is an analytic subset, which is enough for our purposes. So here, the fact that it is an analytic subset is due to the fact that actually the integrability is completely encoded into the vanishing of the nine-noise tensor of J. Okay. And also from the very definition of compatibility, you get that for any J, you can associate a Kähler metric on the complex manifold Mj, which is given by the composition of omega Nj. Okay. Okay. now we are going to study like the geometry of this infinite dimensional manifold given by all of these compatible almost complex structures. And in this infinite dimensional manifold, I mean, this is the setting where we would like our moment map to appear. And in order to do that, we need to find a symplectic form on this infinite dimensional manifold. And actually, I mean, we are lucky because it turns out that this space of almost complex structure admits a natural tautological Kähler structure, which is defined as follows. So first of all, you look at the tangent space of this manifold at a fixed point, where here with a point I mean an almost complex structure. And it is easy to see that actually this tangent space can be identified with the set of those endomorphisms of the real tangent space of the manifold that verifies some compatibility with omega and with J. So in particular, you ask that these endomorphisms U, which corresponds to a tangent vector, anticommute with J, and it is skew symmetric with respect to omega. Okay, now in this tangent space, you can define a complex structure, which is tautological in the sense that it is just the compositions with the complex structure J, which is the point that you are considering the tangent space at. Okay. Then you can also define a Riemannian metric on the tangent space, which is by definition just the L2 metric induced on the manifold by means of the Kähler metric Gj. Okay. And then by taking the composition of the tautological complex structure and the tautological Riemannian metric, you can cook up a symplectic form capital omega. Okay, well, actually, it can be directly checked that the Hamiltonian group, the group of Hamiltonian diffeomorphisms acts on this space of compatible almost complex structure by pullback. The analytic subset of those almost complex structures that are integrable is invariant under this action, and also the tautological Kähler structure on this infinite dimensional manifold is also invariant under this group action. Okay. So indeed, we are in good shape to state the Donaldson-Fujiki theorem, which tells you that the scalar curvature is actually a moment map for the action of the Hamiltonian group on the infinite dimensional manifold of compatible complex structure endowed with a tautological symplectic form. So to be more precise, I mean, we can associate to any complex structure, okay, a function which is the scalar curvature of the Kähler metric obtaining by J and the form omega that we fixed at the beginning. This function is moot. It is equivariant with respect to the action of the Hamiltonian group, and it also verifies a formal moment map equation, which means that if you take the integral of the differential of mu at a point J applied to a tangent vector field times the Hamiltonian potential of an Hamiltonian vector field, then this is given by this is equal to up to a constant to the tautological symplectic form applied to the tangent vector and to x star j. So here, let me be a bit more precise. So here, x star j, let's say x star is the fundamental vector field on the infinite dimensional manifold associated to x. And you can actually, I mean, it can be explicitly computed, and it turns out that x star at the point j is nothing but the Lie derivative of minus the Lie derivative of j in the direction of x. So here, this is actually a true moment map equation, I mean, at least formally a moment map equation, because if you remember, like the target space of the moment map should be G star. So here, G, the Lie algebra G, is the Lie algebra of Hamiltonian vector fields. But we can identify, so here, let's say up to a constant, the Lie algebra of Hamiltonian vector fields with the Lie algebra, with the space of smooth functions via the correspondence that x goes to its potential. And actually here, you can also identify the space of smooth functions with its dual by means of the L2 product induced by the symplectic form omega. So this is like really, like at least formally, a moment map equation for the Hamiltonian action on the space of complex structures, and it has like very important consequences in Kähler geometry. So for examples, I mean, it gives you a unified view of some different problems. So for examples, you can see lcK metrics are zeros of mu. So here, when I say zeros of mu, I mean that, of course, mu is defined up to a constant. So here, when I say zeros of mu, I really mean like mu equal to a certain constant, okay? So in this sense, this corresponds to the standard constant scalar curvature Kähler equation. And also, the Calabi extremal Kähler metrics can be seen as the critical points of the L2 norm of mu, okay? And from the GIT perspective, the Hilbert-Manford criterion, which is an algebraic criterion that relates the stability of orbits to the analysis of the eigenvalues of some operators. This motivate. I mean, as I said before, I mean this is just a formal moment map equation in a sense, so you cannot really apply them directly, but this motivates the notion of K-stability. That it is a crucial notion when you study, for example, Kähler-Einstein metrics on Fano manifolds. Well, the idea now is, okay, so everything up to here holds just for Kähler geometry. So the idea now is to ask whether we can hope for a generalization of this nice Donaldson-Fujiki framework in the realm of Hermitian geometry. So when I say Hermitian geometry, I mean like triple MJ omega, where omega is not necessarily closed. So as far as I know, I mean, this is very optimistic and far from being reached up to the moment. But the first natural setting when you can ask whether you can get a moment map framework as Donaldson-Fujiki did, is the framework of locally conformally Kähler manifolds. Because this, like in a sense, this is the closest possible condition to be Kähler in the non-Kähler setting. And I mean, of course, as we heard yesterday in the introductory talks, well, locally conformally Kähler means that it is an Hermitian metric such that around each point of the manifold you can find a neighborhood and a local conformal change that turns this omega into a Kähler form in that neighborhood of the manifold. Okay, so the idea now is to try to mimic the Donaldson-Fujiki construction to this non-Kähler setting and see whether we can find we can find a moment map and what are the conditions that allows us to cook up a moment map. Well, first of all, whenever you fix your you fix your compact manifolds, okay, you need to fix a true form. Now, since we don't want our space of metrics to be Kähler, these forms that we're gonna fix is not gonna be symplectic, but it's gonna be locally conformally symplectic, which means that omega is non-degenerate, and that again around each point of the manifold you can find a local conformant change that turns omega into a closed form locally. Okay. Well, by the Poincaré lemma, these local conformal changes can be organized in a globally defined one form theta called the Lie form that verifies this equation, so that the omega is equal to is not zero, but is equal to theta wedge omega up to a certain constant, which depends on the normalization you choose, actually. And this theta, the Lie form has to be closed. But of course, again, I mean, if theta is zero, then you end up into the symplectic framework, so that you already know what happens. due to Donaldson Fujiki. And if theta is exact, again, you get a global potential, like a global conformal change to a symplectic form. So for the purpose of this talk, we're going to assume that theta is not exact, so that we really work in non-Kähler setting, in a sense. Well, this can be, I mean, this condition can be rephrased as follows. So, I mean, whenever you have a locally conformal symplectic form, you can consider the universal cover, and you can pull back the form to universal cover. Then the pullback form is going to be globally conformal to a symplectic form on M hat, which is the universal cover, and the deck transformation group acts on the symplectic cover by homotheties. So as we heard yesterday, this is a full characterization. This can be given as an alternative definition of being locally conformally symplectic. And well, now the first things to do is to choose like a symmetry group with respect to which we want to search for a moment map. So in the Donaldson-Fujiki framework, the natural symmetry group was the group of Hamiltonian diffeomorphisms. Here in this locally conformally symplectic framework, the symmetry group that we decided to study is the so-called group of twisted Hamiltonian automorphisms. And the definition of twisted Hamiltonian automorphisms can be given as follows. So we look at those diffeomorphisms of the manifolds that leads to the universal cover to a diffeomorphism of the universal cover which preserves the symplectic structure on the universal cover. Okay, so whenever a diffeomorphism does this job, we say that it is twisted Hamiltonian. And again, I mean, this is an infinite dimensional generalized Lie transformation group on the manifold, and we can compute directly the associated Lie algebra of this transformation group, and it follows that the infinitesimal transformations are precisely those vector fields that have a potential, like in the symplectic case, but this time the potential H is not with respect to the exterior differential operator Z, but is with respect to the twisted operator d theta. So here, d theta is the twisted differential that you obtain by taking the differential d minus 1 over n minus 1 theta wedge. Okay, and whenever a vector field verifies these conditions, we say that the vector field is twisted Hamiltonian, and this is the set that we are gonna focus on. Okay, and well, again, so if you remember in the Donaldson-Fujiki framework, the idea was to look at those almost complex structure that were compatible with omega, and then we defined a tautological Kähler structure on this infinite dimensional manifold. And here the good thing is that we can do like the same construction even in this locally conformally symplectic framework. So again, you can consider like the set of those almost complex structure on the manifold that are compatible with omega. Actually, the definition is the same. So the fact that omega is not closed plays no role here. You can define again the analytic subset of those complex structures that are integrable, and surprisingly, you can define again the tautological Kähler structure. So I say surprisingly because actually, like, I mean, the definition of the tautological Kähler structure, if you remember, does not use the fact that omega was closed. And the point is that it is really like the form capital omega that we get with that construction remains symplectic even if the little omega on the manifold is non-closed. So this is important because, of course, if you want to if you want to produce a moment map in a certain sense, you need a symplectic form somewhere to compute the moment map. And so the first good, I mean, the first good news is that this capital omega works also in this locally conformally symplectic setting. Well, again, you can check that the group of twisted Hamiltonian diffeomorphisms acts by pullback on the space of almost complex structure. The analytic subset of those that are integrable is again invariant, and again, like for any J that you pick into this set, you can associate to this J a Riemannian metric by taking again the composition between omega and J, and this Riemannian metric is going to be non-Kähler, of course, but it's going to be locally conformally Kähler. Okay, so I mean, so which means that again, around each point you can find a conformal change to a Kähler metric. Well, I mean, up to this point, everything seems to work fine, which is good. And so, like the aim now is to find an explicit moment map for the action of the twisted Hamiltonian diffeomorphism group on this infinite dimensional manifold. Well, if you remember, in the Kähler case, the role of the moment map was played by the scalar curvature, which is the trace of the Riemannian curvature tensor. Here, since we are working on a manifold which is non-Kähler, in general, it is common to change connection. So the point is that the fact that a metric is non-Kähler means that the Levi-Civita connection does not leave J parallel. So in a sense, it does not encode the complex geometry of the manifold. So in order to write down this moment map, we change connection, and there's a bunch of Hermitian connections that you can pick on a given Hermitian manifolds. There's a famous work by Baudouchon about that, and basically he described a whole family, a whole one-parameter family of this connection, which is a fine line passing through two distinct points that are the Bismuth connection and the Chern connection. So for the aim of this talk, we're gonna focus on the Chern connection, which is defined by the following formulas. So this is a linear connection that leaves both J and J parallel and coincide with the Levi-Civita connection if and only if the underlying metric is scalar. This connection is characterized by the fact that its torsion has vanishing one part, and it is related to the leaf form of the manifold, because the leaf form theta that we saw before is nothing but the trace of this Chern connection. And this equality here justify the choice of putting 1 over n minus 1 on top of the equation of lcK at the beginning, because we wanted, I mean, in a sense, we want you normalize theta to be precisely the trace of the Chern connection. Well, by taking the trace of the curvature tensor here, you get a function which is called the Chern scalar curvature, which is a non-Kähler analog of the Riemannian scalar curvature. And in a sense, this is like a natural candidate to be a moment map. So in a sense, we would like to express a possible moment map mu in terms of some functions coming from the torsion, so some function coming from the leaf form, and the scalar curvature, the Chern scalar curvature. Okay, so actually, it turns out that there are some. If you try to do computations, like to express a possible moment map in terms of these two ingredients, it turns out that some problems arise. So in particular, the first problem is that the group of twisted Hamiltonian diffeomorphisms of the manifold does not preserve omega. So the point is that it preserves the conformal class of omega, but not omega itself. And as a consequence, if you try to write the map that associate to a complex structure the chance scalar curvature of the corresponding lcK metric, then this map is not going to be equivariant with respect to the action of the twisted Hamiltonian group. And another consequence is that the lifted action of the Hamiltonian group on the infinite dimensional manifold of complex structure does not preserve the tautological two-form capital omega. So in a sense, this seems that it's not a good framework to opt for getting a moment map. There's also another problem, which is maybe less philosophical but more concrete, is that whenever you write the linearization of the chance scalar curvature, then at some point you're gonna get a term which is the Levi-Civita connection of the leaf form, and it seems to us that it was not possible to handle this term by an absorption scheme by adding some terms on the torsion. So in a sense, we would like to get a function satisfying a certain equation, but there was this term that we weren't able to handle. So in order to overcome these two problems, so the fact that the Hamiltonian action does not preserve capital omega, and the problem with the linearization of the chance scalar curvature, the idea is that you can add in a natural way extra symmetries to your problem. So the extra symmetries comes in the following way. So whenever you have a locally conformally symplectic structure on the manifold, okay, you can consider the leaf form, and you can consider its symplectic dual, which is a vector field. So actually here, the fact that omega is not truly symplectic is not important, because you just need omega to be non-degenerate. So actually you get this vector field, which is canonically associated to the locally conformally symplectic structure, and you consider the flow of this vector field, which is a one-parameter group of diffeomorphisms, and you consider the closure of this flow. So the closure of this flow is going to give you an abelian group of diffeomorphisms on the manifold that we call T. So actually, you need to make some assumptions on this group here. So the first thing is that you would like this group to be compact. So this justify the name T, because whenever it's compact, then you get a torus. And here, notice that the fact that this group obtained as a closure of the V flow is compact can follow from the existence of an almost complex structure which is compatible to omega, which is preserved by V. This is because, of course, whenever you have such a complex structure, then you get a corresponding Riemannian metric, and this V is going to be a killing field for the corresponding Riemannian metric. So by the Myers-Stirnov theorem, this T will going to be a closed subgroup of a compact group of isometries. So in this case, T is going to be compact. So this is a geometric. This is like a geometric. How you say? Property that can assure you that this T is compact. The second condition that you need to impose on the torus is that this torus acts by Hamiltonian diffeomorphisms. So notice that when the flow itself is closed, so that T corresponds to an S1, this is automatically satisfied, because actually the symplectic dual of the leaf form is by definition a twisted Hamiltonian vector field. So because it has a potential, and it is just a computation. But in general, as far as I know, it's not known whether the twisted Hamiltonian diffeomorphism group is closed or not. So in general, if T is higher dimensional, is not for free that the whole group acts by twisted Hamiltonian diffeomorphism. So these are like the hypotheses that we need on this torus action on the manifold. Then whenever you have this torus, we focus on the T invariant framework. So it means that instead of looking at the whole group of Hamiltonian diffeomorphisms, we look at those twisted Hamiltonian diffeomorphisms that commute with the torus. Instead of looking at compatible complex structure, we looked at compatible complex structure that are invariant under the action of the torus. And instead of looking at C infinity functions, we look at C infinity functions that are invariant under the action of the torus. And so actually, whenever you pass to the invariant framework, you realize that first of all, the group of twisted Hamiltonian diffeomorphism that commutes with T actually preserves omega. So it solves the first problem. So the map that assigns the scalar curvature to a J is going to be equivariant, and the lifted action by pullback is going to preserve the tautological symplectic form on the infinite dimensional manifold. And not only that, but the problematic term that appear in the linearization of the Chern scalar curvature turns out to be orthogonal to the tangent space of those complex structure that are T invariant. And so in particular, it plays no role at all in the moment map equation. So we get rid of it. Well, actually, by means of this remark, we were able to prove the main theorem of this work, which is that under these assumptions, like the map that defined on the space of integrable, compatible, complex structure in that takes one of these complex structure and gives like the Chern scalar curvature or the corresponding metric plus a certain multiple of d star theta is actually smooth, equivariant, and it verifies the same formal moment map equations that we saw in the Donaldson-Fujiki framework. So here again, as in the Kähler case, we are identifying the twisting Hamiltonian vector fields that commute with T with a space of invariant functions by taking X and associated its potential, and we are also identifying C infinity, which is dual by means of the L2 product. Okay, and so we were able to find an explicit formula for this moment map. So actually, from this moment map framework, we also get as an immediate corollary a Futaki type invariant. So namely, we get the following corollary, so that whenever you take the integral of mu j over the volume is a number which is independent on j, so it is a constant actually, and the map defined on the Lie algebra of the torus into R that associate to a vector field X on the torus, like the integral of the product of the potential of X times mu minus mu bar is actually constant itself. And I mean, this is like this is just an immediate corollary of the moment map equation, because by assumption the torus lies inside the twisted Hamiltonian vector fields, and since we are working on the space of complex structure that are preserved by the action of this torus, when you lift the action on the infinite dimensional manifold and you consider the infinitesimal fundamental vector field associated to this action, then this is automatically zero. Because if you remember, the X star was nothing but minus the Lie derivative of J with respect to X. Okay, so in particular, if you go back to the moment map equation, well, whenever you put X into the Lie algebra T, the right-hand side vanishes directly. So that's why you get that this function and this number are independent on J, at least in its connected component of the space of compatible complex structures. Well, actually, I mean, the good point of having this moment map is that it can lead further notion of canonical Hermitian metrics in the non-Kähler setting. So here the point is that whenever you study an Hermitian non-Kähler manifold, it's not trivial at all to understand like what are the good notions of best metric that you can put on the manifold, because you have a bunch of connections, you have also torsion terms coming into play. So it can be seen like as a sort of geometric way to find a good notion of canonical metric in this setting. And also via the GIT machinery, this can also lead to the construction of the corresponding moduli spaces. Actually, the vanishing of the Futaki type invariant is an obstruction to the existence of T-invariant lcK metrics, such that the corresponding equation mu equal a constant is satisfied. So here, I mean, we got this constant mu equation, and the problem for I mean, this is a work in progress actually, with Daniele, Cristiano, and Joshua Guindare. Actually, the problem here, in order to understand like the solutions to this equation, is that up to now there is not a good cohomological or geometric interpretation for the constant that should be put inside the equation in order to find a solution. So this is something we are working on right now, and it's not clear. I mean, the constant would be this constant here appearing in corollary B, and it's not clear how to handle it. And another things to say is that if you remember, whenever you have this locally conformally symplectic manifolds, you have a symplectic cover, but the moment map we found on the locally symplectic manifold does not coincide with the scalar curvature on the symplectic cover. So this is really a feature of the lcK geometry in a sense. And finally, of course, I mean, in the Weismann case, so where Weismann means that the Lie form is parallel with respect to the Levi-Civita connection, well, this equation that we found, like it just corresponds to the constant scalar curvature equations on the Weismann case. Yes, and I think that this is all I wanted to say.